Reminder that Chapter 8 tends to be one of the more, well, I think probably in my opinion, it's the most challenging thing we do in second semester. So beginning wise, the start, it's not too bad. We just have a lot of like vocabulary, but from a complexity stuff, not too bad. But by the end here, this is a pretty deep, big chapter. In the second half of this chapter, I think there's some pretty challenging ideas and applications, and the procedures that we need to use can be kind of time consuming, and it's have to be careful about that we're paying attention to kind of what we're doing, because it's kind of easy to get lost in the process. So the big important thing for you guys right now is that the notation, the vocabulary that we're going to be dealing with here in the beginning is really important to making sure that we're able to communicate effectively these more complicated ideas in the second half. So even if this seems kind of all right, whatever, name, symbols, try to do your best to kind of absorb this now. It'll make the second half considerably easier if you're not also fighting through the vocabulary and the notation at the same time. You know what I mean? And I'm not trying to scare anybody. I'm just trying to, we're trying to do our best. So I just want to, kind of preload this with a little bit of advice so that we can do a nice job. You know what I mean? Okay. All right. Today we're going to be talking about section 8.1, which is about two-dimensional vectors. So we'll start with just some definitions here. So when we talk about a two-dimensional vector, that's an ordered pair of real numbers which represent both magnitude and direction. So a vector quantity has two parts, has a magnitude part and a direction part. And hopefully a little bit of this seems familiar. You did this in geometry, or honors geometry anyways. I know that was 2 years ago now, so it's probably a little bit foggy, but a little of this vocabulary should come back. When we talk about representing a vector, there's actually lots of different representations we can use to represent a vector. And we're going to look at many of those here in this chapter. The most common representation is probably this component form. So we'll represent our vector v. Now, when we're typing, to type a vector, we're going to write it as a boldface letter. When we write it with our pencil, we'll put a little vector hat on top of it. And then this wedged bracket we're going to use. So that's going to be our symbol to let us know that what you're looking at isn't an ordered pair. It's not like a point. It's not an interval, but this is representing a vector, right? Because we've seen lots of things where you have one number, comma, another number, right? It's not a set with two elements. It's not a point on the XY plane. It's not an interval from one number to another number. It's a vector. And we call these quantities A and B the components for that vector. So typically we'll name these components the same way we would an ordered pair. So we have an X component and a Y component, where A is the X component and B is the y component, right? So if we wanted to, another common way we'd represent a vector would be by drawing a picture of it. We call this like the standard representation of a vector. So if I take one of these component forms, let's do that. So let's say we have the vector 3, 5. If I want to draw its standard representation, because it's in component form, we understand that the tail of the vector is at the origin, and the head of the vector is at the point 3, 5. So 3 over and 5 up. So when we draw the head of the vector, we put an arrow at the head. And we draw the tail of the vector, it's just like the point. It's like the start of a ray. So the vector ended at that point, 3, 5. Is everybody okay with that idea? The key here is when we have a vector in component form, it's understood that the tail of our vector is always at the origin. That's the big takeaway. So when we talk about a vector having two quantities, we said before those two quantities are called magnitude and direction. If I talk about the vector here, the magnitude of the vector is going to be equivalent to the length of this arrow that we just drew. So, and we have a special symbol that we use to represent the magnitude of a vector. Clip that in. And we use that vertical bars around the vector to represent the magnitude. Now this is probably getting kind of irritating because we've used that double, like the two vertical bars, to represent a lot of different things, right? It can be the absolute value of a number. It could be the cardinality of a set. And now, or it could be the determinant of a matrix. I think we use that notation in your Algebra 2 textbook. And now it can be the magnitude of a vector. How can I tell from the symbols just which one of those the vertical bars are representing? Depends on the thing that's on the inside of it, right? If the vertical bars are around a vector, we're talking about magnitude. If it's around a matrix, we're talking about a determinant. If it's around a number, we're talking about absolute value. If it's around a set, we're talking about cardinality, right? So the context is going to be, or the meaning of those vertical bars is going to be implied from the context, right? Everybody's okay with that? So I just want to recognize that it's worth pointing out that there is no such thing as the absolute value of a vector. That's not a thing. So don't get confused on that. I know the initial response is like, oh, vertical bars, absolute value. Not if it's around a vector. There's no absolute values of vectors. It's a magnitude. Okay. The other part of a vector is its direction. So the direction of some vector is the direction the arrow is pointing using standard position angles in the XY axis. So if we go back to that picture that we drew just a moment ago, the length of the vector is the magnitude, and this standard position angle would be like the direction for the vector. Everybody's okay with that? Same standard position angles we dealt with when we graphed or when we drew angles in first semester, right? Works the same way. The terminal side is going to be the vector. The initial side is going to be the positive side of the x-axis. We're going to be rotating counterclockwise, just like we did for standard position angles in first semester. Everybody so far so good? So again, a lot of just vocabulary, a lot of notation being thrown at you. I'm trying to go through carefully. So I'm just kind of talking about these things so we have a chance to absorb what's going on. So suppose that we have we've talked about vectors can be represented in component forms, but they don't necessarily have to. Suppose we have the vector we have the vector that starts at the point 3, 6 and ends at the point 5, 9. So if we drew that going up by 2's, we'd be talking about this vector, right? What if we want to take this vector and translate it to a vector in component form? There's going to be a reason we want to do that, and will come in section 2, but component form makes everything we want to do with a vector way easier. What we're going to want to do here is we're just going to translate this vector. So we'd want to move the points left 3 and then down 6. So we can translate that vector so it's back at the origin. And then this point, the translated version of that point, will be the component form for our vector. Everybody's okay with that idea? So all that said, this just basically boils down to the formula, or to a formula. So let's drop that in. But that's the idea of what we're doing. This formula we call the head minus tail rule. So we say if we have some vector whose has the initial point at x1, y1, that's the tail of our vector, and the terminal point at x2, y2. To convert it to component form, we just do x2 minus x1, comma, y2 minus y1, which is exactly what we would have been doing here. We would subtract 3 to move it over, and then subtract 6 to move it down, right? Exactly what we're doing in our drawing that we just saw a moment ago. So this should feel, now that we've seen the picture and talked about exactly what this is doing, a very natural transformation. All we're doing is just translating, left to right and then up or down some amount. The amount would be the initial point, right? So whatever the initial point is, we're going to translate the opposite direction in the x and the opposite direction in the y. oops, sorry. So let's drop in an example here that we can do. So here it says, show that the vector from A to B is equivalent to the vector from X to Y. What are we going to do that? Or what do, well, I guess let's retract here for a minute. Let's think about what does it mean for two vectors to be equivalent? Braden? So they'd have the same component form, i.e. the same magnitude and the same direction, right? So those two statements are equivalent. So all we're going to do is we're going to translate the vector AB to component form and the vector XY to component form and see if they're the same. So the vector AB is going to be head minus tail. So it says from A to B. So this is the head and that's the tail. And we'll do the same thing for XY. Again, it says from X to Y. So again, X is the tail and Y is the head. Bless you. So what would we say here? Are these two things equivalent? Yeah, because they have the same component form. Everybody's okay with that? So we'd say that like AB is equal to XY. All right. Everybody feel good about how I can take a vector described as two coordinates and translate it into component form? Now, the reason we want to have this is that everything we're going to do, calculation-wise, is going to be derived from component form vectors. It just makes all the calculation that much easier. Let's begin by illustrating that. So let's say that we have some component form vector. Just call it, vector V. If I want to calculate the magnitude of that vector, the magnitude's the same as the length of the vector. In geometry, how would I calculate the length of that segment? What tool did we use to calculate the length of a segment? I thought I heard somebody whispering it. Starts with a D if you need to be brave. The distance formula. That's exactly right. So we're calculating the distance from 0, 0 to the point X comma Y, right? Well, what's the distance formula? Well, it's the square root of x2 minus x1 squared plus y2 minus y1 squared. And since we're doing this for a component form vector, the x1 and y1 is always the origin. So this just turns into x squared plus, or the square root of x squared plus y squared. So dropping this in, again, this is our formal definition from the notes. And we'll do a quick example here. So for part A, again, we're asked to find the magnitude of the vector. Notice in part A, the vector is given to me in component form. So all I need to do is the square root of x squared plus y squared. And I'm done. In part B, notice that the vector is given to me as a tail and a head, a coordinate for the tail and a coordinate for the head. I have two options here. I can either use the distance formula with the points that I'm given, or I can convert this vector in component form and then use the other formula. This is exactly the same thing. Notice inside the distance formula, that looks like the x coordinate for component form. That looks like the y coordinate for component form. So it literally 6 of one, half dozen of the other. You know, it's doing the exact same thing. I like just converting everything into component form personally, because I find that more often than not, if there's anything else I need to do, I'm pretty glad that I had it in component form to start with. So that's usually my what I do there. No, the square root of 98 is not a perfect square, but we can simplify that one. We couldn't simplify the square root of 29 because that's a prime number. How can I simplify the square root of 98? Just a quick review. (98) is 49 times 2. The square root of 49 we know is 7. So best answer would be 7 root 2. So again, you're just looking for perfect squares when you're simplifying. So is it divisible by 2, or divisible by 4, by 9, by 16, 25, 36, 49, bingo. Or I could have just observed here that this is going to be like 49 plus 49, which is literally 2 times 49, which is really what I was looking at, but that would not always be the case. But yeah, all I'm really doing is looking for perfect squares there. Okay. So what about, so we've seen how to get, given a vector, how to find its magnitude, correct? What we still need to do is, given a vector, how do we find its direction then? Right? Because those are the two components that are the two quantities that describe a vector, our magnitude and direction. Here's the good news. You already know how to do this. You already know how to do this. And you're going to say, I don't know about that, Mr. Kulik. I'll say, sure you do. Let me drop in and we'll do a numeric example and show you that, yeah, you already know how to do this. All right. So let's say we want to find the magnitude and direction for this vector v that's described by location for the head and the tail. So I'm going to start just by writing the component form for vector v. So head minus tail, head minus tail. Everybody's good to there? Oops. Should be -7 though, Mr. Kulik. I would have caught that. Don't worry. So if I want the magnitude out of this, again, it's in component form, so it's no big deal. So 64 plus 49 is 113, and I don't think that has any factors that can simplify out. To get the direction now, what I'm going to do is I'm going to draw a picture. I'm going to plot the point, -8, 7. I'm going to draw this as a standard position angle. Whose point there is -8, 7. So I know then that this angle theta is going to be 180 plus this angle phi. Exactly what we did in first semester. Righteous. So we'll say theta equals 180 plus phi. And then to calculate phi, we're going to do tan inverse of y over x, but we're going to do the absolute value. Remember, we always do the absolute value of the stuff inside of phi. And then it's just calculator time. Notice that we're using degrees here to describe directions for vectors. That's the standard. Typically, we wouldn't use radians to do this. So if you didn't like radians, good chapter for you because you won't see many of them. Great. So 180 plus tan inverse 7 over 8. I'm just doing the absolute value in my head here. Everybody's okay with that? Rather than going through and pushing the buttons on the calculator, I can drop negative signs easier than all the buttons it takes to do that. Oops. And I want to make sure that I'm in the right mode. So I was in radian mode, so I'm going to switch out to degree before I press enter there. So I have 221.19. Isn't that nice when the procedure here is the exact same procedure that we already learned? That happens a lot in second semester, particularly after this chapter. There's like 3 other chapters after this where it's like, oh, this is still like the exact same thing we did before. So we've seen how to take a vector and obtain its magnitude and direction, correct? What if we want to do the opposite now? What if we want to take a magnitude and direction and get back a component form vector? Let's see an example of doing, or what we'd have to do that. So let's say that we have, like we have vector v. We know the magnitude is, let's call it just c. and the angle is like, I'm just going to call it, the direction is just going to be theta. So what I could do is, if I think about the picture, I can draw some standard position angle theta. Everybody agree with that? And on that terminal side, I can find a segment with length C, and I would be looking for this point, and that would be the same as my component form for the vector, right? Okay, well, if I think about this as a right triangle, my x side would be the same thing as cosine theta equals x over c, adjacent over hypotenuse, or x over r, if we're thinking about it as the point definition. So if I just multiply both sides by that constant, the x-coordinate is just going to be c times cosine theta. How would I find the y-coordinate? Shockingly, or not surprisingly, it's going to be c times sine theta. And what is c again? The magnitude of the vector. What's theta again? The direction that was given. So this is all I need to drop that into component form. Does this remind you of anything? Remember when we did those navigation story problems? This was the exact same formula we used there. Could it have been us working with vectors at that same point? We didn't even realize it? Oh my goodness. Isn't it nice when it just comes back around again? Maybe you're not happy because you didn't like the vector story problems, or those navigation story problems, but it is nice that we'd seen it before. And this is not difficult, right? Because you're given the magnitude and you're given the direction, all you do is plug it into a formula. The x-coordinate is magnitude times cosine direction, which is easy to remember because on the unit circle, cosine is x. So to get the x component for my vector, I use cosine. And likewise, on the unit circle, sine is y. So to get the y component of my vector, I need to use sine. It's easy to remember, right? I love it. I love it. I love it when things just like, where it just is what it should be. You know what I mean? It's like I'd expect cosine to go with the x, and it does, and sine to go with the y, and it does. And it's like everything makes sense. It fits my expectation. That'll be easy to remember for me. Let's do a quick numeric example. So we want the component form for vector u, whose direction is 224 and whose magnitude is 5. So it's nothing more complicated than plugging it into the formula we just kind of derived. And then it's calculator time, homie. So we have negative 360, comma, negative 347. And that's it. Does that answer make sense? Well, if I think about a 224-degree angle, should be in quadrant 3, x and y's are negative, Seems pretty reasonable to me. You guys buy that? That's an easy little just check to make sure you have the right quadrant. But that's an easy thing to check. It just takes like literally, 10 seconds to draw the picture. All right. How are we feeling so far? Is this okay? There's a lot of vocab, but like the computation stuff that we're doing, really simple, right? Nothing is like a bunch of steps. Nothing is really complicated. The formulas are relatively easy to use and hopefully pretty intuitive after we've kind of talked through where they're coming from. So the next thing we're going to talk about is vector operations. So when I talk about vector operations, we're talking about like, how do we add? Can we add or subtract vectors? Can we multiply vectors? Can we, can we write a vector equation and solve it? Can we do these kinds of things, right? So we're kind of building out the algebraic structure now that we've built out this quantity, this vector quantity, right, that has magnitude and direction, and we have like a couple of ways we can represent it, either with a picture, described as a magnitude direction, described as the location of the head and the tail, or this component form. Now, like, what kind of algebraic structure does a quantity like that have, right? Can we write an equation with it? Can we, what does adding and subtracting mean? Does multiplication even make sense? Does division make sense? That's what we're going to be doing in this next section, is kind of building out that structure. Okay? So when we talk about just like adding and subtracting for real numbers, the first thing we need to establish is like an identity element. When we add and subtract real numbers, what's the identity element for that? What number can I add to something else that doesn't do anything? 0, right? So what we need to do there now is to define what we mean by a 0 vector. If we're going to have addition and subtraction for vectors, we need to have something that kind of acts the same way that the number 0 does. Everybody cool with that? So we can do that. So the way what we define that as, so we call it the 0 vector. We represent it with a letter. What letter are we using? It's the letter O. Why do you suppose we picked the letter O? It looks like the number 0. That 0 vector is the component form 0, 0. That's a vector with magnitude of 0. And it has no direction. This is the only vector quantity that we have that can have no direction to it. Is everybody okay with that? This is not surprising that the component form 0, 0 is what we're going to use as the 0 vector, right? No one is shocked by that. So now let's talk about like what if we wanted to add two vectors together, what would that really mean? So let's say we take a component form vector here and a component form vector there, and we wanted to add those two things together. What are we really doing? Well, I'm going to take the tail of my blue vector and translate it so that the tail of my blue vector is at the head of the red vector. Everybody's okay with that? And then this vector in green, we call the resultant vector. And that vector would represent the sum of the red vector and the blue vector. Does this look like anything? Remember when we did the navigation story problems and we drew the picture for kind of what was going on? The very first one where you're like, oh my God, this is like horrific what you're doing right now, and like so many little details on the picture, and then it all kind of went away. So at the end of the day, if I want this point here, how did I get to that point? Well, I took the x-coordinate of the red vector and I added to it the x-coordinate from the blue vector. Everybody agree with that? And similarly, to get the y-coordinate, then I took the y-coordinate from my red vector and I added to it the y-coordinate from that blue vector. Oh, okay. So what this means simply is that if I'm adding two vectors in component form, I just add them component-wise. I add the x-coordinates together, I add the y-coordinates together, and that's going to be my resultant vector. Was this exactly what we did when we did the navigation story problems? Right? Like we created a vector for like the wind and a vector for the boat, and then we just added the two vectors together component-wise. Holy smokes, I love it. It's all stuff we've done before. Okay. So if we can, okay. So the next thing we're going to do is we're going to talk about, so we've seen that vector addition is really just like a translation, right? Right, I'm just translating two vectors and then finding the resultant. Okay. Another geometric transformation we had was also like dilations, right? If I dilate a vector, what's that equivalent to doing to it? It's going to be like stretching it out or shrinking it down, right? What's going to change? The magnitude, but what's going to stay the same? The direction, almost. And we'll explain why in just a second. So if I do that, do you remember how we did a dilation in geometry? Is you multiply the coordinates by some factor, right? If it's the same factor, then like nothing changes. It just stretches it out. So that's exactly what we're going to do here. We're going to define an operation called scalar multiplication. So the scalar product of a vector and some real number is just multiply that real number to both the x component and the y component. Now, we call that real number a scalar because it's scaling our vector, right? Now, if that real number is positive, your resultant vector is going to have the same direction. What would happen if that real number was negative? The direction is going to change to be the opposite direction. Basically, your arrow is going to go from pointing this way to pointing that way. But like close enough, right? Close enough to keeping the direction the same. All right. So if I wanted to define then vector subtraction, how could I do that? Addition of two vectors where the second vector is multiplied by the scalar -1 What is this equivalent to? Subtracting being adding the negative? No. So if I have scalar multiplication and I have vector addition, I can create vector subtraction from those two pieces, right? That's all I'm saying. Let's do a couple of numeric examples just to kind of feel a little bit at home with this. Oh boy, that is not where I wanted that to go. Try it one more time, Mr. Kulik. So U is the component form vector -2, 4. V is the component form vector 7, 3. And we want to calculate U plus 2V. So doing that first. So there's my U. And then I have 2 times V. Now, which operation should come first? The scalar multiplication or the vector addition? Same order of operations as for real numbers, so we'll do the scalar multiplication first. Absolutely. And then we'll add the vectors. No big deal, right? So this is our answer. Everybody happy there? If I wanted to do 4V, well, there's only one operation going on there. So there's that. And then we have 5V plus -3U. So 5V plus -3U. So again, just like before, what comes first? The multiplication. We're going to call that, make sure we call that scalar multiplication. At least that's what I'm going to say every time. And be careful to say that, because it turns out we also have another kind of multiplication analog that has another name. So just being careful here. And now we can just add the two vectors. And there's our answer. Everybody okay with that? So again, we've talked about geometrically what scalar addition looks, or vector addition looks like. Just to give you an idea of what scalar multiplication looks like. So like if this is vector V here, if I want to graph 4V, it's basically we're just stacking 4 of these V's right on top of each other. Because for real numbers, like 4 times 3 is the same as adding 4 together 3 times. So like 4 times vector V is like 4 vector V's just stacked one on top, added one on top of each other. Yeah, of course. So far, so good, everybody? Okay. Again, nothing too complicated is happening, right? It's just like a lot of different symbols, a lot of new vocabulary. I'm trying to make sure that we're kind of stepping through this carefully because it can be a lot if I just like race through this. It's one of those things where this feels very easy and then you get to the homework and you're like, what the heck was that thing again? What the heck was that mean again? What the heck, you know, like... and you spend too much time, or it becomes hard because you're just spending all your time like going back and looking up what something means again. Okay. So what we're going to do now is formalize a point that I made earlier. So we talked about for real numbers, adding the negative is the same thing as subtracting, right? So like 5 minus 4 is the same thing as 5 plus negative 4. Now 4 and negative 4 have a relationship to each other. The name we call, or the name we give those two numbers, we call them additive inverses, because when you add them together, we get the identity element, which was 0. Everybody's okay with that? So to be real formal about vectors, we need to define what we mean by an additive identity, or additive inverse there, which we already said. What did we say we're going to call the additive inverse for a vector? Just scalar multiplying by -1, which is all we're saying here. So now clearly, like, vector u plus negative vector u is going to give me the vector 0, 0, right? Everybody agree with that? Any vector I pick, that's going to be the result, right? You could have any coordinates you want. If you add u with negative u, that gives you the vector, the 0 vector. Everybody agree? Okay. So because that property works, that's what we're going to use to define scalar vector subtraction. And again, when you multiply by that -1, the direction becomes the direction of our vector after we multiply by -1. What happens to it? It would now have opposite direction, right? So if my direction was 45 degrees, what would the new direction be? What will opposite direction mean? Like, we know visually what it means, but let's talk about numerically how to get to it. So let's just think about a picture, right? If you can't see it, that's okay. So like 45 is here, right? So when I swap directions, it's going to be here. Everybody agree with that? What is this angle from there to there? 180. So to find the opposite direction, we're going to either be adding 180 degrees or subtracting 180 degrees, right? If your number's smaller than 180, we're adding. If your direction was bigger than 180, you would subtract. But that's the idea. If you want that opposite direction quickly, without having to think about it, you're just either adding or subtracting 180 degrees. Does that feel okay? And again, it was obvious, but you had to look at it the right way, right? When we draw the picture and look at what's going on, it's like, oh, yeah, okay. Adding and subtracting 180, sure, I should have been able to see that. But you didn't, because it was your first time, and that's okay. That's why I'm here, right? So you don't have to like spend a half an hour thinking about something that turns out to be like, oh yeah, if I just looked at it that way, it's easy. You know? All right. Now we're going to define another very special vector. So we have this special vector, the zero vector, right? And we have these special vectors, the additive inverse. The next special vector we're going to talk about is called the unit vector. And we say that a vector is a unit vector if and only if its magnitude is 1. So if a vector has length 1, we call it a unit vector. Or any vector with length 1, we call a unit vector. So what does, if I think about drawing any vector with length 1, you know, like if I draw all possible, where are their terminal points all going to lie, or the head point? That's all on a circle with radius 1. So what are we really talking about here? The unit circle. Look at this. It's all just coming right back again. So it turns out every unit vector is of the form cosine theta, comma, sine theta. Not surprising there. Well, every component form unit vector is of the form cosine theta, sine theta. Whoa! So, if I want to find the unit vector that's in the same direction as some other vector, what would I need to do? So let's say we have some vector v here. And what I want to do is I want to find this unit vector here that has the same direction as v, but is only 1 unit long. What operation am I going to be doing looking at this picture? This is going to be a scalar multiplication problem, right? Because I want the direction to stay the same. I just want to shrink it. Or in some cases, I guess if it was a really short vector, I'd stretch it a little bit. But more often than not, we're talking about shrinking because like Mr. Kulik isn't going to give you like 0.01 comma 0.61 as your vector to try, you know, like that's dumb looking. Like that's annoying to have the decimals like that. Okay. So what scalar would I need to multiply v by to end up at u? What's the length of v? It's that, right? What would I need to multiply that by to turn it into 1? It's reciprocal. 1 over the magnitude of v. Does that feel okay to everybody? So what do we say there then? Let's kind of formalize this all into a definition. So given some vector v, to find a unit vector u in the same direction as v, u is going to be 1 over the magnitude of v times vector v. Let's do a numeric example just to kind of drive that home. So what am I going to need here to find u? I need the magnitude of v. How do I find the magnitude of v again? The distance formula, or since it's in component form, it's really just, you know, the square root of the component squared, right? Oops, not 41, dum-dum. 25 plus 36 is 61. Try again. Everybody's good with that? So to get my unit vector u, I'm going to multiply by vector v by 1 over square root 61. And then we'll rationalize our denominators, because typically we don't like to leave the square root in the denominator. And there's my unit vector. What's my check that I should do to make sure I did that right? Let's just check to make sure that the length of this is indeed 1. Sound good to you guys? So I'm just going to use my calculator to do that, because it's going to be kind of an annoying by hand computation. And at that point, I'm pretty convinced that I did that right. So again, this last piece at the end on the calculator is just me checking to make sure the vector that I created did have length 1. And I know it's going to be in the same direction as u, because all I did was scalar multiply it by a positive, which I know conserves direction. Everybody feel good? Okay. All right. What do we have? We have, oh, this just keeps on going and going and going. All right. We got 10 minutes. Okay. I'm going to do 2 more ideas, and then we're going to stop for the day. Sound good to you guys? You're like, yes, please. Okay. So we're going to talk about 2 special unit vectors next. Any guesses as to what those 2 special unit vectors might be? How about 1, 0, and 0, 1? Right? We call those 2 the standard unit vectors, and we give them a name. We call the vector 1, 0 I, and the vector 0, 1 j. And what these standard unit vectors allow us to do is you can now take any vector and rewrite it as the sum and scalar product of unit vectors. So what we did here is, if we have some vector CD, I can rewrite that as the vector C0 plus the vector 0D. Right, if I add those together, I get CD again. I just separated an X-only vector and a Y-only vector. Everybody's okay with that idea? It's the equivalent of, like, when we drew things on the unit circle, we thought about, broke it into an X part and a Y part. The same idea. Everybody's cool with that? Okay. Now, using my definition of a scalar multiplication, I can factor a c out of this. So c divided by c is 1, and 0 divided by c is 0. So I'm just pulling a scalar out front of c. leaving me with a unit vector. And I can do the same thing over here, leaving me with another unit vector. And then again, I is the name we give for the unit vector 1, 0. So I wrote CI. And J is the name we give for the unit vector 0, 1. So I wrote DJ. This representation of a vector has a name. It's called the linear combination form. And at this point, this doesn't allow us to do anything neat right now, but in the future, this becomes a helpful representation. So for right now, all you really need to worry about is like, can I go back and forth between a component form vector and a linear combination form vector? Which is really easy, right? You just take the components and put an I on the X component plus, and then a J on the Y component. Or you take the coefficient in front of the I and the coefficient in front of the J and turn them into the X component and the Y component. Woo! Super tough, right? All right. We're going to stop here. The next thing up is going to be talking about dot products. That's going to be our other analog to multiplication with vectors. So we have scalar multiplication, and we're going to have this dot product operation. But that's for next time. We're not going to get into that now. For you guys, what can we do? Up to 22 seems good. Well, you could do some other stuff too, but let's just wait. And yeah, 22 seems good. Oops, that's not what I wanted to press. Is that due this week, though? No. When will that be due? Yeah, that Sunday after. Do we have anything due this week? I don't think so, right? We checked everything in review included last week, right? So I think we're good. How's that feel? It's a fun Sunday. Nothing to worry about. At least math-wise. I mean, I'm sure you have other things to worry about. The state of the global economy, the environment, whether I have a date to the winter formal or not. There's lots of things to worry about. But your math homework, not so much. All right. Enough jokes from me.